Welcome to this comprehensive guide on optimizing game performance in Unity 3D by offloading expensive AI and pathfinding calculations. Understanding the need for multithreading is the first crucial step in this optimization journey. Unity primarily operates on a single main thread, which is responsible for rendering graphics, processing user input, and executing all game logic. When complex calculations, such as advanced AI behaviors or intricate pathfinding, occur on this main thread, it can lead to significant frame rate drops. This often results in the game freezing or stuttering, severely impacting the player's experience. By offloading these intensive calculations to a separate background thread, the main thread remains free to handle critical real-time operations. This ensures a smoother, more responsive gaming experience without interruptions. It's crucial to distinguish between threads and coroutines, as they serve different purposes in Unity. Coroutines are excellent for asynchronous operations, allowing tasks to be spread out over multiple frames. However, it's important to remember that coroutines still execute on the main thread. A single, time-consuming operation within a coroutine will still cause the entire application to freeze. Threads, conversely, are managed by the operating system and can run concurrently on different CPU cores. This true parallelism prevents the game from freezing, as heavy computations are isolated from the main game loop. A key challenge with threads in Unity is that most Unity API calls must be made exclusively from the main thread. This limitation adds a layer of complexity to managing data and results between threads. Now, let's begin by setting up our project in Visual Studio and Unity. First, create a new Unity project, which will automatically generate the necessary project files. Once the project is created, open the C# project solution in Visual Studio. This allows us to write and manage our code efficiently. Next, within the Unity editor, we'll set up our game environment. Create basic game objects to represent the scene, such as a ground plane and walls, defining the playable area. Then, add a nav mesh to the scene to define the walkable areas for our AI agents. Finally, create a player character for the AI to interact with, providing a target for pathfinding. Now, let's dive into implementing multithreading for our pathfinding. We'll use the system threading namespace to create and manage our background threads. To start, instantiate a new thread object, passing the method that will contain our pathfinding logic. Then, call the start method on your new thread to begin its execution. The calculate path method will encapsulate all the pathfinding logic. Crucially, this method should not directly interact with any Unity API functions. When passing data to your calculate path method, such as start and end positions, use value types or deep copies. This prevents data corruption that can occur when multiple threads access the same reference type simultaneously. Since Unity API calls must be on the main thread, we need to synchronize results back. Tools like Unity Main Thread Dispatcher or Invoke are essential for sending pathfinding results safely to the main thread. This ensures that any updates to Unity objects happen in a thread-safe manner. To prevent race conditions when multiple threads access shared data, implement thread safety using locks. A lock statement ensures that only one thread can access and modify a specific block of code or data at any given moment. This critical section protection maintains data integrity across threads. Let's explore common pathfinding implementations. The A** algorithm is a popular choice for pathfinding, known for its efficiency. It works by dividing the map into nodes and calculating the cost to move between them. A heuristic function estimates the cost from a given node to the target, guiding the search efficiently. Alternatively, Unity's built-in nav mesh system offers a robust and easy-to-use solution. You simply bake the nav mesh to create a walkable area based on your scene geometry. Then, attach a nav mesh agent component to your AI agent. Use agent.setDestination to command the agent to move along the calculated path. Let's look at some practical code examples for both threaded pathfinding and nav mesh usage. Here's an example of a pathfinding class demonstrating threaded pathfinding. Notice the using system, threading, and Unity Main Thread Dispatcher for managing the thread and synchronizing results. The calculate path method simulates a long-running operation with thread sleep. After calculation, the path result is enqueued to the main thread for safe access. The update method then visualizes the path once it becomes available on the main thread. For NavMesh, an AI controller script simplifies agent movement. It uses getComponent NavMesh agent to get the agent reference and start. In Update, if a target is set, agent.setDestination continuously updates the agent's path. Here are some helpful tips to keep in mind when working with multithreading in Unity. First, always avoid calling Unity API functions directly from background threads. This is a fundamental rule to prevent errors and crashes, as Unity's API is not thread-safe. Second, utilize thread-safe data structures when sharing data between your main and background threads. These structures handle synchronization internally, reducing the risk of race conditions. Third, regularly use the Unity Profiler to identify performance bottlenecks. The profiler helps confirm that multithreading is indeed improving your game's performance as intended. Finally, be mindful of garbage collection when creating and destroying threads frequently. Excessive garbage generation can lead to performance issues, even with multithreading. By following these guidelines, you can effectively offload expensive AI and pathfinding calculations. This approach significantly improves game performance and provides a much smoother experience for players. Thank you for watching this tutorial on optimizing Unity 3D game performance. We hope this guide helps you create more responsive and engaging games.